Okay friends, so here we are going to solve another example on rotational dynamics. This is from H.C. Verma. Rotational mechanics, it is page number 199. Unsolved example number 66. This is based on the principle of work and energy. So let me first explain the principle of work and energy, and then we will go ahead with the problem. The principle of work and energy is to be applied between 2 points, between two reference points, say point 1 and point 2. Suppose the velocity at point 1 is v1 and velocity at point 2 is v2, then we will say that the change in the kinetic energy is equal to work done. So what is the change in the kinetic energy? It is half into m into v2 square minus v1 square. In addition to this, suppose there is some rotational motion involved, then the change in the kinetic energy will, due to rotational motion, will also have to be considered. Half I omega 2 square minus omega 1 square is equal to work done. Now there are only three types of work that we have to consider. Only three types of work have to be considered. So which are the types of work we consider while applying the principle of work and energy? The types of works that we are going to consider is, number 1 is the work done by weight. If the weight is coming down, the work done is positive, and if the weight is going up, the work done is negative, because when the weight is coming down, you are doing work in the direction of acceleration due to gravity. It is taken as positive. Number 2 is work done by friction. It is always negative, because it always opposes the motion, and it is simply given by force of friction into displacement. And the third is work done by spring. If x1 is the initial elongation, that is difference between the original length and the natural length, and x2 is the final elongation at stage 2, that is again change in length upon original length, then the work done by the spring is given by half into k x1 square minus x2 square. It is, sometimes my pen doesn't work properly. It is half k x1 square minus x2 square. Please note, no sign conventions are required here. It is simply x1 square minus, don't forget x1 square minus x2 square. If it comes positive, it is positive, comes negative, it is negative. But just as we have used sign conventions here, no sign convention should be used while work done by the spring. It is just half k into x1 square minus x2 square. K is the force constant of the spring. So using this principle, now let us try to solve this example. Let me draw the figure for you. This is H.C. Verma sum number 66. There is a pulley. One end of the pulley is attached to a spring. and it goes to the ground. On the other end, a mass is hung which is 1 kg. The radius of this pulley is given as 0.2 meter and its moment of inertia is also 0.2 kilogram meter square. The force constant of this spring is 50 Newton per meter. The force constant of the spring is given as 50 Newton per meter, and we are supposed to find the speed of the block after it descends through 10 centimeter. After it descends through 10 centimeter, the system is released from rest, so the initial velocity is 0, and also initially the spring is in its natural length. So initially x1 is 0. So x1 is 0, and after it descends through 10 centimeter, so x2 will be 10 centimeter, that is it will be 0.1. Okay, let me redefine the problem here. There is a pulley whose radius is 0.2 meters, whose moment of inertia is 0.2 kilogram meter square. One end is attached to a spring with a force constant of 50. The other end attached to a block. The system is released from rest. Initially the spring is in the free length, it is not elongated, it is in the natural length. We are supposed to find the speed of the block after it has moved down through 10 centimeter. We are going to apply the principle of work and energy here, and we are going to find out the speed of the block. So let us do it step by step. Let us first find a change in the kinetic energy. What is the initial kinetic energy? Initial kinetic energy is 0 because the system is released from rest. So the initial kinetic energy is 0. What is the final kinetic energy? The final kinetic energy is the kinetic energy of the block plus kinetic energy of the pulley. What is the kinetic energy of the block? The kinetic energy of the block will be half m into v square, where v is the final velocity, and kinetic energy of this pulley will be half r omega square. So let us find it out. So this is half sometimes the pen is really tricky. Let me erase this and let me go to the next page maybe. Okay, so the kinetic energy is half mv square plus half I omega square, which is half mass of the block is 1, velocity we don't know, plus half moment of inertia of the pulley we know 0.2, omega square is v square upon r square, and radius is again 0.2. So this gives me v square upon 2 plus, what is this, please calculate this, 1 by 2 and 0.2, so 0.4. 0.4 is 4 by 10, that is 2 by 5, so 5 by 2. 5 by 2 plus 1 by 2, 6 by 2 square, that is 3v square. So the change in the kinetic energy is 3v square, right? This is the change in the kinetic energy. Now we'll find the work done. Okay. Number 1 is work done by the weight. As the weight is descending, the work done by the weight is positive. So it is m into g into h. Mass is 1 kg, g is 10, and h is 10 centimeter, which is 0.1. That gives me 1 joule. Number 2 is work done by spring. Which is half into k, x1 square minus x2 square, which is half into 50. As the spring is originally in the lateral length, x1 is 0, x2 is 10 centimeters, so it is 0.1 ka square. That is minus 25 into 1 by 100. That is minus 1 by 4. So total work done will be 1 minus 1 by 4. That is 3 by 4 joule. Now we'll simply equate change in the kinetic energy and work, right? So you can see the change in the kinetic energy was 3v square. Right? The change in the kinetic energy we had obtained as 3v square, which we had just obtained. So just equate change in the kinetic energy with work done. Let me erase this. Change in the kinetic energy was 3v square and work done is 3 by 4 joules. That gives me v square as 1 by 4, that is v as 1 by 2. So this is your final answer. The velocity of the block is 1 by 2 or 0.5 meter per second. Let us see if the answer is matching. Problem number 66 it is. I am checking the answer. The answer is 0.5, correct. So here we have applied the principle of work and energy. Again, from engineering point of view, this is an extremely important concept and you must follow that. And please remember, only 3 types of work is required to be taken: work done by the spring, work done by the weight, and work done by the friction. Work done by the tensions in the cords are not to be considered. Please remember, while applying work energy principle, the work done by the tension in the cord or tension in the spring is not to be considered. Work done due to elongation of the spring is this, half k x1 square minus x2 square, that has to be considered. But work done due to tension must not be considered while applying the principle of work and energy. Okay, that's it.